Hello everyone, here we'll be discussing homogeneous equations of higher order. Essentially what I'll be discussing today is a continuation of what we saw last time with homogeneous equations and the characteristic equation. Right, so let's recall first what we saw in the previous video in regards to that. If we have this second order linear constant coefficient homogeneous equation, ay double prime plus by prime plus cy equals 0, the characteristic equation of this equation is the quadratic ar squared plus br plus c equals 0, and the solutions to this equation actually relate to solutions of the differential equation. How they relate kind of depends. We broke that up into cases, and we'll discuss that in a moment, but first let's see some examples to figure out how this really works. And let me just say that in general this works. So if you have this general homogeneous equation of some order that's higher than 2, for instance, and here a sub n minus 1 and a sub 2 and all the way down to a sub 0. These are real coefficients, let's say. Just like a, b, and c we assume to be real coefficients. I guess they could be complex, but that gets a little hard to examine when it comes to the third case. So for just to make things kind of simplicity for our scenario, we'll be looking at only the coefficients being real, if that makes sense. Now again, in general, this differential equation has a characteristic equation, which is kind of what you'd imagine it to be. Just replace all of the y with however many primes with r to that power. So y double prime goes to r squared, much like, I don't know, y to the n would go to r to the n. And there should be a y here. Sorry about that. This corresponds to no power. Just like here, cy corresponding to just c in the polynomial equation. Okay, awesome. Now, let me say that the cases for this generalization are inherited from the cases we have seen already. So think back to the three cases we saw for this second order type of equation, where either the solution has two distinct real numbers, one repeated real number, right, multiplicity 2 if you remember that, and two complex conjugate solutions. So those were the three cases, and we'll actually explore that in a little bit afterwards. But right now, let's take a look at this example, and let's see where to go from here. So based on my generalization here, what is the characteristic equation for this differential equation? So let me write CE for characteristic equation. How many primes we have dictates the power of r. So y triple prime corresponds to r to the third, y prime corresponds to r to the 1. Perfect. And again, if there's no prime, then it corresponds to just a constant itself. Great. So now, what does this mean? Well, how do we solve this type of polynomial equation? In this case, we can factor out an r. And what we're left with now, r squared minus 1 can actually be factored. As the difference of squares, it's r minus 1 times r plus 1. And then by the zero product property, ZPP for short, we end up getting that r is either 0, positive 1, or negative 1. Which should make a lot of sense because this r being 0 means r is 0, r minus 1 being 0 means r is positive 1, r plus 1 being 0 means r would be negative 1. And that's pretty simple to check. Now, what does this correspond to? Well, if you recall the cases we saw from the previous video, if you had distinct solutions like we do here, that means for each solution, you have a constant times e to these solutions times x. So any linear combinations of those will actually be a solution. So in this case, our general solution then must be y equals c1 e to the 0x, e to the 0x, e to the 0, which is just 1. So I'll just write c1 here, plus c2 e to the negative 1x. I guess I'll do positive. Let's do it in the same order. So positive 1x, that's just x, plus c3 e to the negative 1x, or e to the negative x. There we go. That is our general solution to this three-order differential equation. Wow. So what this tells us is that really to solve these kinds of equations, we have to be pretty good at solving polynomial equations. So we may need to look back at some algebra techniques throughout some examples we'll be seeing. So let's take a look at some of these general cases as I was talking about earlier right now. Right, so here I'm going to try my best to describe what happens depending on how our solutions look to our characteristic equation of the differential equation we're looking at. So here I say given that r equals r naught is a solution to the characteristic equation of a constant coefficient linear homogeneous equation, then the following holds. So I break it down into two scenarios. One, if r naught has multiplicity m, then x to the n times e to the r naught x is a solution, so let me underline that a, it's a solution of the differential equation, where n is an integer. If you haven't seen this before, this means n is an integer. So specifically it's a positive whole number because it must be in between 0 and m minus 1. Of course, m is multiplicity. Multiplicity is a positive whole number amount, the amount of times something repeats as a solution, essentially. Okay. Now, why this is the case is a little hard to explain, but if you look back at the, well, I guess it would be case 2, as I described it in the previous video, for a second order linear constant coefficient homogeneous equation. When multiplicity was 2, we said that the general solution was c1 e to the r1x plus c2x e to the r2x. In other words, x to the 0 times e to that solution times x is a solution, and e to the 1 times e to that solution of the characteristic equation times x is also a solution. So basically the power of x can be 0 or 1 in that case because the multiplicity was 2. You see that? So whatever the multiplicity is, any power of x multiplied by e to that solution of the characteristic equation times x, as long as that power goes from 0 to 1 less than the multiplicity, that would also be a solution. We'll actually see an example of that shortly in this example. And the second thing I say is something we should already know. If r naught is complex, and again, the coefficients of our original differential equation are assumed to be real numbers, and then this actually ends up being true. If r naught is complex, say r naught is equal to alpha plus beta I, then alpha or e to the alpha x times cosine of beta x and e to the alpha x times sine of beta x are solutions to the differential equation. And this of course means that any linear combination of them, hence y equals c1 times this plus c2 times that, will also be a solution, as we saw in case 3 from the previous video. So a lot of these ideas we'll kind of use together, but first what I want to do is solve this example here. And the way I'm going to do this is first convert to a characteristic equation. And the characteristic equation, of course, is going to be r to the third minus 3r squared. Let me draw this in black. Write this in black, actually. So it's r to the third minus 3r squared plus 3r minus 1 equals 0. Now, there are a few ways of doing this. Essentially, what you can do is you can, well, I mean, it depends, but if you have a good eye for these sorts of things and you see and notice these binomial coefficients, 1, 3, 3, 1, and you notice alternations of the signs, positive, negative, then you know this must be r minus 1 all to the third power. Essentially, from pattern recognition and knowing binomial theorem well, there's a way of connecting that pretty straight off the bat. There is also something known as the rational zeros test, which we probably have seen way back in algebra, which says that any factor of the constant term in a polynomial divided by any factor of the leading coefficient in that same polynomial is a possible rational zero. Now in this case, factors of -1 and factors of 1, if you divide those, you just get plus or minus 1. So those are possible solutions. And you see, if you plug in positive 1, does that work? Well, if you replace all of the r to the powers of 1s, you get 1 minus 3 plus 3 minus 1. Now clearly, -3 plus 3 is 0, they cancel out, and 1 minus 1 also cancels out. So r equals 1 is indeed a solution. What about -1? Well, that actually won't work, because if r is equal to -1, then all of the odd powers become negative and all the even powers stay the same sign. So in other words, we would have -1, minus 3, and minus 1 like that. And this actually doesn't, notice there's no cancellation at all, they're all the same sign. So this actually just amounts to -8, not 0. So r equals -1 doesn't work, but r equals 1 does work. And another result from algebra is that if r equals 1, if r equals 1 is a solution to a polynomial equation, then this implies that r minus 1 must be a factor. Okay? So if you actually work out dividing this polynomial by r minus 1, then you'll get another polynomial, and then you'll actually find out that 1 is a solution to that, and so on. And in fact, that's really the way of doing this. I don't have space to show that. We'll actually see something similar in the next example, but for right now, just take my word for it that this is indeed the case. And since the power here is 3, then that means r equals 1 is a solution with multiplicity 3. Perfect. And now according to this first statement here, what does that mean? What can we conclude? Well, we can conclude that a power of x times e to the 1x is a solution where that power of x goes between 0 and 1 less than 3. So between 0 and 2. Namely, we have the linear combination of such terms, c1 e to the x. Notice e to the x because this is e to the 1 times x, our solution is 1, plus c2 x e to the x, plus c3 x squared e to the x. So I hope we see how I'm getting that. Now each of these e to the x's, x e to the x, and x squared e to the x are of this form. This first term has the power 0, this has the power 1 for x, and this has the power 2 for x. Notice, since the multiplicity is 3, the powers float in between 0 and 3 minus 1. And then, of course, any linear combination of these solutions is itself a solution. So this is what we say is the most general solution to this equation. Awesome. So now we're going to look at a particular type of example where we'll explore that rational zeros test I was talking about just now. All right, so in order to get started here, let's find the characteristic equation of each of these. I'll just start with the first example, of course. So the characteristic equation of this differential equation is r to the third minus 3r squared, squared because it's double prime. There's no y prime, so that means we don't have an r term. And then 4y contributes a 4 to this polynomial equation. Awesome. But now how can we solve this cubic? I want to basically factor, but that's going to prove difficult. What I want to take advantage of is the rational zeros test, or RZT for short, which basically says that factors of the constant term, which by the way, factors of 4 are 1, 2, and 4 itself. Factors of the leading coefficient are technically just 1. And the possible rational zeros, according to the rational zeros test, are factors of the constant term divided by factors of the leading coefficient, with plus or minuses, so you could have possible sign change. So now here are possible rational zeros from the rational zeros test. Each of these divided by 1 is just these in themselves, but with plus or minuses. So we have plus or minus 1, plus or minus 2, and plus or minus 4. And we can actually check by just plugging them in. If you try to plug these in, there's only 3 numbers here, so it's not too bad. But let me just tell you, if you plug in 1, for instance, well, 1 won't work because you end up getting 1 minus 3 plus 4, and that's going to be positive 2, not 0. Negative 1 actually works. Negative 1 cubed is negative 1. Negative 3 times negative 1 squared is still negative 3, so that's negative 4, plus 4 is indeed 0. So negative 1 actually works. Okay, positive 1 didn't work, but negative 1 worked. Now, if r equals negative 1 works, then this implies that r plus 1 must be a factor of this polynomial. So if we want to figure out what the other factor is, well, we can just try to piece it together a little bit possibly, or we can even use polynomial division, like long division or synthetic division. It wouldn't be hard to do it that way. You have to look into that a little bit. Instead of doing that though, I'm just going to piece it together. R times r squared must give us r to the third. 1 times 4 for the last term must be positive 4. And the middle term must, okay, so it's going to involve r, but it must be negative. How do I know that? Well, everything inside is positive. If this was positive, then there wouldn't be any negative terms when multiplying, but there is a negative term. So this must be negative. And if you call it AR, for instance, you can kind of try to combine some things here. And if you FOIL this out, you get r cubed minus AR squared plus 4r. Distribute the 1, you get r squared minus AR plus 4. Adding these together, you end up getting r cubed plus 1 minus a times r squared plus 4 minus a times r plus 4. Now I know this sounds a little funny, but believe it or not, it works, right? In order for us to have no r term, that must be 0, so a must be 4. And in fact, if a is 4, 1 minus 4 is negative 3. So that works, and that means a is 4 here. So that's just a way to piece it together without using any type of special polynomial division, but it wouldn't be a bad idea to look into refreshing on long division or even synthetic division. I may even actually use synthetic division in this example afterwards. But right now, notice that this r equals -1 gave us one factor, and then from there, we're able to see what the other factor is and continue factoring this. Now this is pretty simple to factor. The two numbers are multiplied to +4 and add to -4 are -2 and -2. So what we end up getting is r plus 1 times r minus 2 quantity squared equals 0. So by the zero product property, what do we get for our possible solutions? We get either -1 or +2, but +2, notice, has multiplicity 2 because the power 2 from the corresponding factor. Now, with that being said, what do we know? Well, with that being said, our solution, general solution to the differential equation must be some constant times e to the -1x plus c2 e to the 2x from this one. But the fact that it's multiplicity 2, let's multiply that by another x. So that's going to be c3x e to the 2x. And recall if the multiplicity was more than 2, you would multiply by an x squared, then an x to the third, for additional terms until you get up to 1 less than this multiplicity. But here we stop at 1 because the multiplicity is 2. So I hope that makes sense. Perfect. And that is the solution to this first example. The second example, well, the characteristic equation is going to be pretty simple to find. That's just, it's r cubed minus 3r squared plus 4r minus 12 equals 0. And by the rational zeros test, what do we get for possible rational zeros? Well, let's take a look. Factors of 12, there's actually a lot of them. Factors of 12 are 1, 2, 3, 4, you can divide 12 by 6, and then 12. Yeah, that's a lot. Now how I got this is just running from 1 through 12 itself and seeing which numbers are actually factors of that. In other words, which numbers we can divide 12 by and get an integer. Also, you can say 12 is 6 times 2, 12 times 1, and 3 times 4, and you get all of these intermediate factors. And again, there's just a 1 in front of here, so we're dividing these by 1, just literally getting these with plus or minuses. So that's quite a lot to check, actually. And I'm going to show you, I'm going to actually check these by synthetic division because I think it's a little quicker. Now, if you're not really familiar with synthetic division, what I'm going to right now will maybe look a little weird, but you should have seen it before, so I don't think it's going to be too unfamiliar to us. But I'm going to write a box number here being one of these, and then the coefficients of our polynomial are 1, -3, 4, -12. We'll test 1 first, and let's see what happens. So the rules of synthetic division are you bring the first one down for free, multiply by the box number, add straight down, and then continue the process. So if you multiply by 1, you get 1, add down, you get -2, times 1 is -2, add down, you get 2, times 1 is 2, and these add to -10. Now this remainder is the remainder of the division of dividing this polynomial by r minus this number. So if we're dividing by r minus 1, then that means r equals 1 would have been a solution, but the remainder isn't 0, the remainder is -10. So it's not a solution. In fact, this number -10 is the exact value you would get when plugging 1 into this. Notice plugging 1 in gives you 1 minus 3, which is -2, plus 4, which is +2, minus 12 is -10, indeed. So we want 0 as a result. So I know this doesn't work. But in order to get a 0, notice this has to be 12. We know 1 comes down for free, but we don't know the intermediate 4 numbers here. But now on my list, we know +1 didn't work. We can try -1. Multiply by -1, add straight down. Multiply by -1, add straight down. Multiply by -1, you get -8, not 12. So that doesn't work either. So now let's try +2, let's say. Multiply by 2, add, you get -1, times 2 is -2, add, you get 2, times 2 isn't 12, 2 doesn't work. We can try -2, I know I'm going kind of fast. That times -2 is -2, add, you get -5, times -2 is +10. This is 14, times -2 is -28. That also does not work, geez. Hopefully 3 works, or else this is going to be a long video. But let's see. So when you multiply by 3, you get 3. Add, you get 0 times... Oh, that actually works, because look. So add these, you get 0. 0 times 3 is 0. Add these, you get 4. And 4 times 3 is 12. Perfect. So that actually works. We got a hit. And not only does that work, this is the beauty of synthetic division. These right here are the coefficients of our quotient. So what we have shown is that this left-hand side polynomial factors as r minus our box number solution, which is positive 3 by the way, times the polynomial whose coefficients are 1, 0, and 4 in r. So namely, r squared plus 4. Great. So now what do we know? Well, we know r squared plus 4 actually has no solutions. If you were to set r squared plus 4 equal to 0, you can kind of see this. Subtract 4 to the other side, you get r squared is equal to negative 4. Square root, you get r is equal to the square root of negative 4, which is, well, 2i. So in fact, those are complex solutions. So let me just say from this, we get r is equal to, so from the zero product property, we get r is equal to positive 3 or plus or minus 2i. Now if you don't see that 2i part, I'll write it over here off to the side, let's say. So if r squared plus 4 is equal to 0, subtract 4, we get r squared is equal to negative 4. If we square root, we get r is equal to plus or minus the square root of negative 4. Square root of 4 is 2, square root of negative 4 is 2i. So it's plus or minus 2i indeed. Awesome. So now what? Well, now we have a solution that has no multiplicity. So that means e to the 3x is a solution. And we have this imaginary solution here. Now remember that if we have a complex solution of the form 0, well, alpha plus beta I, in this case it's 0 plus 2i, then e to the alpha x plus sine or cosine of beta x is a solution. So here alpha is 0, but beta is 2. In other words, we don't have to worry about the e part, because it would be whatever's in front of this. So if you had, like, for instance, there was a 1 here, then it would be e to the 1 times x, so e to the x, times sine of 2x, or times cosine of 2x. But since there's technically a 0 there, you have e to the 0 times x, which is, well, that's just 1. So really what we end up getting from this is our general solution must be c1 e to the 3x plus c2 cosine of 2x plus c3 sine of 2x. Perfect. And now we're going to take a look at, I think, maybe 1 or 2 more examples. Right, so I was going to do possibly 2 examples, but then I thought, you know what, we haven't actually seen a initial value problem in the context of this section so far. So let's just do this as our last problem then. So here we have this fourth order differential equation. It's homogeneous of the type we've been looking at. So of course it corresponds to a pretty nice looking characteristic equation, which in this case is r to the 4th plus 6r squared plus 9. And we'll take a look at that soon. But now notice we have these 4 initial conditions. You need 4 of them. Why do you need 4 of them? Well, basically because there's going to be 4 coefficients essentially. Now, obviously the order has to do with how many coefficients you need, or I guess how many coefficients you'll have. In other words, how many initial conditions you need to solve for each of those coefficients. Now, why is that the case? I mean, it kind of has to do with the fundamental theorem of algebra, the fact that this corresponds to a degree 4 polynomial that has at most 4 solutions. And in fact, it has exactly 4 solutions if you consider complex solutions and multiplicity. And we definitely do for these differential equations. So it's nice, we get a really, really nice connection between a lot of things we've seen in algebra when it comes to solving polynomial equations. Okay, so now, there are a few ways we can solve this. We could try to use the rational zeros test. It's not going to work. This actually has no real solutions as it turns out. Spoiler alert. But you say spoiler alert before, right? Well, anyways. Yeah, so, right. Why, how do I know that? Well, before we get to that point that I can explain how I knew that, I guess something we have to do is we have to take a look at some kind of pattern recognition here. So there's a way of factoring this, actually, by what is called the quadratic form. Now, this polynomial is in quadratic form. essentially what you have is you have a trinomial that has a constant term, and then the two powers end up being, well, one's double the other as far as powers go. Whereas this is 2 and that's 4. So there's a substitution you can make. So if we let's say x equal r squared, then notice x squared must be r to the 4th. In other words, if you apply the substitution into this polynomial, you end up getting x squared plus 6x plus 9, and now we've converted this into a quadratic. That's why I said it's in quadratic form, because it's just one substitution away from being a quadratic itself. Now this is totally factorable. Two numbers that multiply to 9 and add to 6 are just 3 and 3. They're both positive. So this actually factors as x plus 3 quantity squared. Perfect. So you may say, okay, x equals negative 3 is a solution, but I want to go a little further. Notice x was equal to r squared, so really we have r squared plus 3 quantity squared. Yikes. So, right, so from each of these, if we set each of these equal to 0, so let's look at r squared plus 3 equals 0. We kind of saw something like this from the previous example. We can subtract 3, we get r squared is equal to negative 3. We can take the square root, we get r is equal to plus or minus the square root of negative 3. The square root of a negative, an I pops out, so this is plus or minus I times the square root of 3. And we have two solutions for each of the r squared plus 3 factors. Since we have two of the factors, that means each of these has multiplicity 2. In other words, the solution by zero product property, which is kind of what I did here, I said each of the factors, which is really just this one, but it's squared, so the multiplicity is 2 for each of these solutions, is the following. We get r is equal to I times radical 3, that has multiplicity 2, comma, we get negative I times radical 3, and that also has a multiplicity 2. So now the question is, how do we handle this? Well, as it turns out, really all we care about is the fact that when you combine these, it's a complex number that's of the form 0 plus or minus radical 3i, or I radical 3, and that has multiplicity 2. So we're kind of combining this into one complex solution with a plus or minus. Okay. Now, what do we know from the complex case? In the complex case, we know we get e to this times x, e to this times x times sine or cosine of whatever is multiplied to I here times x. So in fact, we get both of those, sine and cosine. Okay, so let me just try to tie that together. So we get y is equal to, I get c1 sine of radical 3 times x, we can write parentheses if you want, plus c2 cosine of radical 3 times x. And I know in the past I've written cosine before sine, but it doesn't really matter. In fact, the labeling is arbitrary. So if you wrote it the other way with c1 being in front of cosine, your c1 and my c2 will be swapped, but the value in front of cosine and the value in front of sine will each respectively be the same after applying these initial conditions. And you can try that on your own if you want. Now, we get this because of the complex scenario. But because of the multiplicity scenario, we have to multiply this solution by x. If you recall, that's really what we do. We multiply by a power of x up to 1 minus or 1 less than the multiplicity. Since multiplicity is 2, we multiply up to, 1 power of x, which is just x. So not only do we have this, but we have each of these multiplied by x as well. So we have c3 x sine of radical 3 times x plus c4 x times cosine of radical 3 times x. Yikes. Yeah. And what's even worse about this, I kind of don't even want to do this now, because we need to find y prime, y double prime, and y triple prime, and that's going to be super, super crazy, because we'll have to use product rule twice, here and here. And that's just for the first derivative. For the second derivative, we'll need to do it multiple times. In fact, I may just even do that off screen. So I'm going to attempt to work that out right now, and then let's take a look what I end up getting. All right, so I somehow managed to handle this craziness off screen. Let me kind of explain a little bit what I did. I'm obviously not going to talk about it in too much detail, so if you want to handle that detail on your own, maybe you can possibly do that, but it's a little much, honestly, but I'll explain a little bit. And then after I explain, I'm going to attempt to, not off screen, actually apply the initial conditions to see what equations we get. So now for the explanation. So this right here, what I've arrowed, is the result we got previously. Now I've combined the sine of x's a little bit, or sine of radical 3x's. So I combine the sines, and then I combine the cosines like this and this. So notice what's in front of sine is c1 plus c3x. What's in front of cosine is c2 plus c4x. The reason why I did that is because it allowed me to view the, what happens as a result of product rule a little easier. So we get derivative of this times regular of that plus regular of this times derivative of that. Basically what you end up getting is a bunch of stuff times sine plus a bunch of stuff times cosine. And after combining things and kind of cross-referencing the derivatives of such coefficients, we end up getting this for the first derivative, and then continuing that idea, we get this for the second and this for the third. And I basically triple check my work here just to be sure, because I know it looks kind of funny where we always have a constant missing for each of them, as it turns out. Where you think that, if you start off with 2 and then you move on to 3, your intuition is that four terms would come about, but it actually doesn't end up being the case. Right. So anyways, like I said, if you want to check this on your own, you can, but it was a little crazy. Just a little bit. Now what I want to do is I want to apply these initial conditions. So I want to let x be 0 for each of these. So for the first one, I don't want to use too many arrows, but maybe I guess there's no escaping it. So for the first one, when x is 0, y is 0. And yeah, when x is 0 here, we just get c1 times sine of 0, that's just 0, plus that goes to 0, so we get c2 times cosine of 0, that's 1, so we end up getting that c2 is equal to 0. Awesome, so we get something from the first initial condition right away. What about y prime, for y prime, when x is 0, y prime is negative 1, so replacing all x's with 0, that goes to 0, so we're left with this term, but then since sine is 0, that blows up to 0 anyways for the first term. Here, we'll get that times 1. When x is 0, we end up getting radical 3 c1 plus radical 3. That term actually is 0, my mistake. I meant to write plus c4. There we go. Perfect. So we end up getting this. That radical 3 c1 plus c4 is equal to negative 1. So I kind of smell a system of equations coming about, but I think it shouldn't be too bad. It looks like so far we don't have too much craziness going on here. Now for y double prime, that's 1 when x is 0. And notice we can kind of already tell that the first thing here ends up being 0 anyways, because it's all multiplied to sine of 0, which is 0. So what we really end up getting is, since cosine of 0 is 1, really what we end up getting is all of this without the x term, because when x is 0, that x term is 0. So here I get just that by itself, which is 2 radical 3 c3 minus 3 c2. Okay. Oh, what's really nice about this is we know c2 is 0. So in fact, keeping that in mind, we can actually do some solving. But I don't want to do solving here. What I want to do actually is I want to just figure out what the equations are. We just need one more. Then I'm going to erase the board, write the equations up on top, and then continue to actually solve for the coefficients after the fact. So I'm just going to go step by step, basically. And for the last one, finally, when x is 0, y triple prime is 0 would be 2. So we get 2 is equal to, remember, this whole thing ends up being 0 because of sine. That ends up being 1. There was one of these actually involved x. I just didn't write it. Geez, that's unfortunate. Which one involved x? So now you'll kind of see where my train of thought was. So it's derivative of this times sine, regular of this times cosine, but they get radical 3's. So it would be negative 3 times radical 3 c3x. So this last one has to involve x. Okay, so that last term goes to 0, so we end up getting this, which is negative 9 c4 minus 3 radical 3 c1. Awesome. So now I'm going to circle each 4 of these equations. I'm going to erase everything, write the system of equations of these up on top. I'm going to leave this supposed solution there. We're going to solve the system for C1, C2, C3, and C4, plug back in, and then finally we'll be done with the problem. All right, fantastic. This is the system of equations I was talking about that we end up with. Now I mentioned that since C2 is 0, if you actually substitute that into this third equation, well, C2 is gone, So that means we can solve for C3 by just dividing by the coefficient. So we get 1 over 2 radical 3. If you want to actually rationalize this by multiplying top and bottom by radical 3, we end up getting radical 3 over 6. So I'm just going to leave it like that. I think that looks fine. And, well, what about the other two that we haven't touched here? Notice they both involve C1 and C4. And in fact, I don't think there's a nice way of eliminating things. Well, kind of actually. If we multiply the top by 3, so let me just write that here. So we get this guy plus C4 equals negative 1. I'm going to multiply this by 3. So if you multiply this by 3, you get a 3 in front of this guy plus a 3 in front of that one, and a negative 1 times 3 is negative 3. Now, this one, just leaving it as is, but rearranging the terms, of course, to match the terms, we get negative 3 radical 3c1 minus 9c4 is equal to 2. So now you see why I multiplied the second equation here by 3, so we match the 3 radical 3 with the negative 3 radical 3 coefficient of c1. These cancel by elimination, indicating negative 6c4 is equal to, I guess that's negative 1. So that means c4 is now found to be negative, actually it's positive 1 over 6. So let me actually write this a little nicer. Perfect. So we have C2, we have C3, C4, and finally C1. Well, we can just plug this C4 value back into this. It's a little bit of work, but let's see. We get, and now we kind of have a choice. Let me use the original second equation. So we get radical 3C1 plus C4, which we now know as 1/6, is equal to negative 1. If we subtract 1/6 to the other side, negative 1 minus 1/6 is actually negative 7/6. And then divided by radical 3 finally, we end up getting that C1 is equal to negative 7 over 6 radical 3. And again, if you want to rationalize this, you can definitely do so. And you get C1 is equal to negative 7 radical 3 over, that's going to be 3 times 6, that's 18. Fantastic. So now I'm going to clean this up, erase everything, and then we'll replace C1, C2, C3, C4 with what we just found them to be. All right, so here it goes. We found C1, C2, C3, and C4 to be these. Plug them in, and finally we get y is equal to negative 7 radical 3 over 18 times sine of radical 3x. Nothing for the first term because 0 turns that into no term, to 0 basically, plus radical 3 over 6, x sine of radical 3 times x, plus 1 over 6, x cosine of radical 3 times x. So yeah, well, to me, I was going to say this is a fun problem, but yeah, it wasn't, I don't know, it's kind of hard to say. It was a little difficult, definitely. It was very, very tedious. There's a lot of work involved, but the concept hopefully wasn't lost in my explanation of things, right? You convert this to a characteristic equation, you use algebra techniques to solve, to find out what R is, and then depending on the scenario, you have a certain setup for the general solution, which we have here. Then we take as many derivatives as we need in order to apply the initial conditions, solve, get a system possibly, plug those coefficients back in, and there we go. And that's the most complicated these problems can possibly be. Now, with that being said, that's the end of the video. That's all I wanted to say as far as homogeneous equations of higher order goes. I'll see you in the next video where we'll be discussing non-homogeneous equations. And yeah, that's going to be kind of crazy because we're going to have to do this and more. So I'll see you in the next video for that. Hope you enjoyed this, and I'll see you then.